Phases of matter, physical changes in matter caused by heat energy, solids, liquids, gases, and plasma. Matter can exist in 4 phases: solid, liquid, gas, and plasma. As you go from the solid state of matter over to the plasma state of matter, you are increasing the amount of heat energy in each state of matter. First, we will talk all about solids. The particles in a solid are held together in an orderly fashion with little freedom of motion. To entirely stop the motion, the temperature would have to be reduced to absolute zero, which is 0 Kelvin, which is also negative 273 degrees Celsius. Notice that in a solid, the particles are held tightly together. They are in a fixed position. Solids have the least amount of energy of all the states of matter. Most solids are composed of atoms arranged in a crystalline lattice. A crystalline lattice is a repeating network of particles. These particles vibrate back and forth in place. So notice the crystalline lattice in this picture. The pattern of purple, green, purple, green, purple, green repeats itself over and over again. That orderly arrangement of solids is called a crystalline lattice. A crystalline lattice is made up of unit cells. A unit cell is composed of the repeating 2 or more atoms that make up the crystalline lattice. The unit cell in the above crystalline lattice would be composed of a purple atom and a green atom that are basically copy and pasted over and over and over again. Allotropes of carbon. Allotropes are 2 or more forms of the same substance. For example, carbon graphite and carbon diamond are composed of all carbon atoms. Graphite found in pencil lead and synthetic oil is soft due to weak bonds between the hexagon layers. So there are these hexagon layers that are heaping these carbon atoms together, but the layers between them are very weak. So when you write with a pencil, you are basically stripping a hexagon layer of carbon atoms onto your paper. Diamond, which is also made up of carbons, has stronger bonds between the hexagonal patterns. So instead of having weak forces between these layers, there are very strong bonds between all of these layers here, which causes diamond to be strong and the hardest substance known to man. How are diamonds and gold measured? A 1-carat diamond has a mass of 0.2 grams or 1/5 of a gram. A carat gold, spelled with a K, is 1/24th part gold. Most rocks are composed of crystal. Amorphous solids. While most solids are crystalline, there are some solids like clay, glass, plastic, and wax that are amorphous solids. These solids do not have a crystalline lattice and any order amongst their atoms or molecules. There is no set arrangement of particles, which causes them to be softer and able to sort of mesh and move around with more flexibility. So the properties of solids is that they have a definite shape and a definite volume. They are usually the most dense of a substance. Water is an exception, where water's solid state, which is ice, is actually less dense than its liquid state, which is water. Of the 4 phases, solids have the least amount of heat energy. All about liquids. When a solid is heated to its melting point, the crystalline lattice starts to break apart. The particles gain more energy and they are allowed more freedom to move past each other. The particles are now free to move. The particles in a liquid are not held together in a rigid pattern and can move past each other. The particles in a liquid are still close together. This is the reason why both solids and liquids are not compressible, but gases are. Gases, which are spread apart like this, if you compress them and cause them to go into a smaller space, the particles in a gas will compress into that smaller space. But liquids and solids are already close enough together that they will not compress like gases do. Properties of liquids. Liquids have a definite volume, but no definite shape. If you take 100 milliliters of water in a graduated cylinder and you pour it into a square plastic container, the volume of that water does not change. It will still be 100 milliliters, but the shape changes based on its container. Liquids are usually less dense than solid, but more dense than gases. Their particles are free to move about, and they are produced by heating a solid to its melting point. Viscosity of a liquid. Viscosity is the resistance of a liquid to flow. The more resistance to flow, the higher the viscosity. Things that are thicker and harder to flow, such as maple syrup, shampoo, oil, honey, things that are thick and hard to flow have a high resistance to flow, and therefore they have a higher viscosity. Things that are easier to flow, that are more liquidy, like water or alcohol, have a low viscosity. Motor oils protect an engine from wear and tear due to friction between moving parts. Motor oils are rated by their viscosity. A motor oil of 10W40 means it has a viscosity of 10 low in the winter and a viscosity of 40 high in the summer. In the winter, when the temperatures are low, the liquid tends to thicken up. And so you want the oil to have a lower viscosity, a more easy to flow liquid at those cold temperatures. In the summer, when the heat starts to thin the oil out, you want that motor oil to have a higher viscosity or a higher resistance to flow. The higher the temperature inside the engine, the hotter and thinner the oil becomes, the higher the viscosity of the oil required. When a liquid's particles gain enough kinetic energy from heat, they are able to break through the surface and the liquid begins to boil. The particles in a liquid cannot escape due to air pressure pushing down on the surface of the liquid. So this is an example of a liquid. This is the barrier between the liquid and the air. Notice that the particles are moving about below the surface of that liquid, and air pressure is pushing down on them. The reason that the particles do not escape into the air is because they do not have enough energy to break through that barrier. As atmospheric pressure decreases, a liquid's boiling point also decreases. So if there is less amount of pressure being pushed down on our surface, so we have our liquid, and instead of a lot of pressure being pushed down, there's only a little amount of pressure, the particles need less energy in order to escape into the gas phase, in order to free themselves and turn them into a gas. So for each 1,000 feet above sea level, the boiling point of water drops almost 1 degree Celsius. Water boils at 75 degrees Celsius on Mount Everest, 95 degrees Celsius in Denver, Colorado, and 100 degrees Celsius in Sarasota, Florida. We in Sarasota are at a lower elevation. There is more atmosphere pushing down on us. So it requires more energy for those particles to break free from their surface than if water were to be put on Mount Everest, which has a lot higher elevation, which means there is less atmosphere pushing down on water at that elevation. As the air pressure decreases, as you get higher, like into the mountains and like on Mount Everest, a liquid's boiling point decreases because they need less energy to break through that barrier. Pressure cookers work on the principle that if you increase the pressure above a liquid, the boiling point increases as well. Raising the boiling point cooks the food faster at a higher temperature. So you have all of this food, you increase the pressure around it. You increase the pressure around it, the temperature at which the food cooks is going to be higher. So you are basically cooking food at a higher temperature so that you can cook it for a shorter amount of time. Some substances like dry ice, which is frozen CO2, have no liquid phase. They go directly from a solid to a gas. The process of going directly from a solid to gas is called sublimation. When dry ice sublimes, invisible CO2 gas is produced. All about gases. Unlike solids and liquids, the particles in a gas are far apart and move at an extremely rapid rate. Another property of gases is that they are compressible, which means that if you take all of these gas particles and try to push them into a smaller space, they will indeed move into that smaller space. According to Boyle, pressure and volume are inversely proportional. What that means is that as you increase the pressure, as you make those particles go into a smaller area, their volume is going to decrease. Inversely proportional means that as one thing increases, the other one decreases. So if you increase the pressure, the volume will decrease. It will be smaller. Gases take up much more space than liquids or solids. This is proof that particles in a gas are far apart, while those in a solid or liquid are close together. Gases have no definite volume or shape. They are less dense than solids and liquids. Their particles are free to move in all directions, hence they take up all the available space in a container. They can easily be compressed since the particles are separated by great distances. Evaporation is a slow process that takes place at the surface of the liquid. So here in this picture on the left-hand side, there are particles in this beaker, water particles in this beaker, and over time, as those particles start to bump into each other, they give each other energy. And eventually, some particles gain enough energy that they are able to break through the surface of that water and turn into the gas phase. Evaporation is a slow process that takes place just at the surface of a liquid. Boiling, on the other hand, the particles turn to a gas, rise to the surface, and break free. So with boiling, you are giving the particles an external energy source, such as heating it on a stove or heating it on a hot plate. So those particles are gaining kinetic energy from an external source. As they bump into each other below the surface of the beaker, they are transferring energy to one another, and then eventually, over a shorter amount of time than evaporation, those particles are able to go from the liquid phase to the gas phase. Boiling is a rapid process in which molecules gain heat energy and go through a phase change to become a gas. The atmospheric pressure is 14.7 pounds per square inch, or 1 atmosphere, or 760 millimeters of mercury. Atmospheric pressure can crush a can if the pressure inside the can can be reduced. All about plasma. Plasma is the fourth phase of matter. Plasma occurs when matter is heated to extremely high temperatures. The atoms lose electrons and become charged particles or ions. So it is the fourth state of matter, but it just means that it has so much energy, so much more energy than gases, that they actually become ions because they are losing their electrons. The stars are made up of plasma, as is lighting. Over 99.9% of the universe is plasma. So it is the most common phase of matter if you are considering the universe as a whole. Plasma on Earth. Where do we see plasma on Earth? Mainly in the form of lightning. The atomic and hydrogen bomb also contain states of matter of plasma. The temperature has to exceed or reach 1 million degrees Celsius or more. Phase changes. So the important thing to remember about this section is that as you go from a solid to a liquid to a gas to plasma, you must add heat energy in order to go from one phase to another. As you go the other way, from plasma to gas, from gas to liquid, liquid to solid, you are removing heat from those particles. During a phase change, there is a change in heat energy but no change in temperature. At the melting point, heat energy is being used to break down the crystalline lattice. At the boiling point, heat energy is being used to convert the liquid to a gas. During an actual phase change, heat is being used to change the phase, not increase the kinetic energy of the particles. It is for this reason that temperature remains constant in a phase change while heat energy changes. The graph explains that. When you go from a solid to a liquid to a gas, in this section right here, you are 100% solid. As soon as the very first droplet of water forms at this point right here, this is a phase change. When you add the heat, you are melting. When you are taking the heat away, you are freezing. But during that phase change, as the solid and liquid are working together and living together in this area, the temperature stays the same. All of that energy, all of that heat energy that is being added is not causing the temperature to rise, but rather it is being used to break down the crystalline lattice. So during a phase change, melting or freezing, the temperature will remain constant. As soon as the last solid has turned into a liquid, you reach this point right here, and then the temperature will begin to rise again. When you get to the boiling point of a liquid, when the very first part of gas forms at this place right here, the temperature again remains constant. During the phase change, whether you are adding heat in for boiling or taking heat away and condensing the gas to a liquid, the temperature stays the same. It is at these points, these flat area plateaus, where the two phases are basically living together. They are working together in those points. So here, you would have both liquid and gas. Here, you would both have solid and liquid. Over up here, as soon as the last droplet of liquid turns 100% into gas, the very last liquid is gone, the temperature will rise again. But the important part to note about this phase change graph is during those phase changes, freezing, melting, condensing, and boiling, the temperature remains constant. And here is just another way of looking at a phase change. As you go from a solid to a liquid, you are adding energy. From a liquid to a gas, you are adding energy, and from gas to plasma, you are adding energy. Let's put it all together. Any pure substance can be changed into a solid, liquid, or gas or plasma by adding or removing heat. A phase change is a physical change since you can change matter back into its original state.